Imagine you're an astronomer, alone in the observatory at 2 in the morning. You're watching raw signal frequencies cascade down your monitor, and then they stop. You're staring at a narrow, precise, repeating transmission, not from Earth. That moment remains hypothetical. Since the very first SETI experiment in 1960, we have pointed radio dishes at the stars and waited. Decades of listening, led by pioneers like Carl Sagan, have yielded 0 confirmed results. For decades, we explained that silence through scale. Humanity has explored a microscopic fraction of the cosmic search space, and we've searched, in cosmic terms, almost nothing. But a 2026 study from EPFL physicist Claudio Grimaldi offers a more unsettling explanation. Grimaldi's mathematical models suggest that alien technosignatures may have crossed Earth's orbit multiple times over the last 60 years, washing over our planet while our instruments were pointed elsewhere. Grimaldi's math suggests the cosmos could be crowded with signals while we remain functionally deaf, scanning the right stars with the wrong detection methods. Our detection methods face a physical barrier. A March 2026 analysis demonstrated that when a radio signal leaves an exoplanet, it doesn't travel through a clean vacuum. It must blast through the violent, dense stellar wind surrounding its host star. This visualization shows the result. What starts as a sharp, single-hertz frequency spike is violently distorted by the turbulence. The signal is ripped apart, arriving at Earth as a weak, unrecognizable band of frequencies smeared out over a wide area. This distortion renders our current tools ineffective. Almost every legacy SETI software pipeline was built to lock on to that clean, intact spike, a feature that physics routinely destroys before the signal ever leaves its home system. Because these fragile radio pulses are so easily degraded, astronomers are shifting their focus to technosignatures that can survive the journey. Researchers at NASA are now modeling how to detect excess infrared heat from Dyson spheres, or the spectral absorption lines of industrial nitrogen dioxide pollution. The search is moving past the hope for a deliberate hello and into the active tracking of the accidental physical footprints left by large-scale industrial activity. We tested this active tracking locally in the summer of 2025. When the interstellar comet 3I Atlas entered our solar system, Harvard astronomer Avi Loeb and his colleagues hypothesized that its unusual trajectory could indicate an artificial origin. The SETI Institute responded immediately, deploying the 100-meter Green Bank telescope. The massive dish analyzed tens of millions of narrow-band signal candidates across 4 frequency receivers as the object made its closest approach to Earth. The search was sensitive enough to detect a transmitter emitting just 0.1 watts of power, roughly the energy required to power a single indicator light on a household appliance. The data showed no artificial emissions. 3I Atlas behaved exactly like a natural astrophysical object, eventually fading back into interstellar space. Despite the negative result, the mission proved humanity can now mobilize global hardware to audit a physical interstellar object in real time. The technical framework for verifying a physical visitor is now fully operational. Modern radio arrays, like the Allen Telescope Array, stream more raw data every second than any human team could review in a lifetime. This volume creates a massive information bottleneck. To manage this, we relied on rigid software that looked for specific mathematical patterns. This created a cognitive blind spot, as we only searched for the signals that human engineers would logically think to send. A new SETI Institute AI system has removed this bottleneck, reducing false positive alarms by a factor of 10. This allows researchers to focus exclusively on viable candidates, rather than chasing interference from Earth's own satellites. The AI is also capable of identifying stellar bycatch, analyzing data from uncatalogued stars that happen to fall into a telescope's field of view during unrelated observations. It searches for patterns we haven't even conceived of yet. By utilizing a machine that does not share our biological biases, we can scan the cosmos without the assumption that an alien intelligence must think or communicate like a human. These new tools have shifted the search for technosignatures from a fringe pursuit into a high-precision scientific operation. Detection is no longer treated as a remote possibility, but as a practical eventuality. This increased likelihood led a task group of ethicists and lawyers to draft the 2026 update to the Declaration of Principles, a global manual for the days following a confirmed detection. The manual establishes rigorous protocols for navigating social media misinformation, ensuring the physical safety of researchers, and coordinating a formal notification to the United Nations. Preparing for this moment has forced astronomers to confront the cosmic mirror. By defining what a technosignature looks like elsewhere, we are forced to see how our own planet appears to the rest of the galaxy. We are already broadcasting our presence. Our military radar pulses into the dark, our industry leaks nitrogen dioxide into the atmosphere, and our city lights are visible from light years away. Humanity is already a technosignature, announcing itself to the void. And now, for the very first time, we have developed the eyes to see who might be looking back.